Okay, so thank you for having me here, and I want to thank the organizers for putting together this great meeting. Renata had asked that I talk about overview of my research codes, sort of the same sort of list we've all been thinking about, and giving the perspective that I just finished my PhD and I'm currently in my postdoc, and what my perspectives are on some of these things. And of course, I want to give a lot of acknowledgments to my PhD advisor, Dane Morgan, and then my collaborators at Michigan, Udo, Rod, and Peter, who all this work is done in collaboration with. So a very broad overview of the types of research that I have done in the past 6 years or so is spin transition, studying the spin state of iron and high-pressure minerals. Dane talked mostly about these yesterday. Doing some general materials research, in particular, looking at superconductivity, the carbon incorporation into MgB2, and then some applications for magnetic tunnel junctions and cobalt iron. And then thinking about things from the D double prime layer deep in the Earth to things that might influence things on the top of the Earth, like Mount Everest, and thermal chronology applications. We've been looking at some helium diffusion in apatite and zircon, where these are in thermal chronology, you can make forward models of the thermal and erosional history of a region, such as the Tibetan Plateau, or and Everest, and these all depend on the kinetics of helium within apatite and zircon. So we can get that from ab initio data. So the common theme with all of these is that it is density functional theory that I've used, even though we are varying from the tops of the Earth to the bottom and somewhere in between. I've also started working with Peter on some geodynamic modeling of 3D subduction zones, and the hope is also just for general information, but to learn in the future to incorporate some, do some more mineral science in these subduction zone regions. So Dane talked yesterday about spin transitions and some of our work here. I'm briefly going to talk about what we have been doing in magnetite. I'm interested in magnetite. Well, magnetite's interesting on its own because it's one of the most common magnetic minerals on the surface of the Earth. And so thinking about high-pressure transitions in that is interesting, but also because there's recent experimental evidence from Ding et al. In PRL 2008, where based on their X-ray emission spectra and their magnetic dichroism, where these results are interpreted as intermediate spin. So this is interesting to a lot of us in this room who have thought about intermediate, or what the spin state is in perovskite. So as many of you know, in perovskite, there is sort of a divide. All of us who have calculated the spin state of iron in perovskite have not found intermediate spin to be stable, but experimental measurements using Mossbauer spectroscopy and X-ray emission spectroscopy have suggest that it is intermediate spin. So magnetite is interesting to me because the X-ray emission spectra in magnetite is showing the same sort of behavior that they observe in perovskite, where the drop of the satellite peak intensity decreases by half, but not totally to zero like they see in low spin for MgO. And so what we have done is looked at the spin states, computationally see do we calculate intermediate spin or something else going on. Okay, so I hope you can appreciate the complexity of the calculations in this structure. Magnetite has octahedral and tetrahedral sites. Iron occupies both of these sites. Iron can have a different valence on these sites. It's 2 plus here and a combination of 2 and 3 plus on the octahedral site. There is the factor of the magnetic ordering and also charge ordering. So there are many influences that have to be considered when we think about the spin state. To make a long story very short, for the purpose of time here, these are purposely meant to be small, but to prove to you that we have looked at all these different factors here, and that the end result, if we look at the enthalpy versus pressure from our calculations, is that iron and magnetite remains high spin up to, for all pressures, and then it undergoes a structural transition to a high pressure magnetite structure where iron is again high spin. So our calculations are not finding intermediate spin in magnetite. So this is consistent with the perovskite calculations. So in these two systems where their X-ray emission spectra shows a drop in peak intensity by a half, interpreted as intermediate spin from experimentalists, we are not calculating intermediate spin to be stable. And briefly, I don't have time to go into all the details about what we have been doing in Appetite, but just talk somewhat about the method. So we're interested in the kinetics. I know Boris alluded to the nudge elastic band method earlier. So what we want is the energy cost of moving a helium atom from one position to another, from one local energy minimum to another within the cell. One way to do this is to just kind of march your atom along your cell, maybe fix it in one direction and allow the structure to relax. But you could have artificially close atoms. What the nudge elastic band method allows us to do is create an artificial spring between these atoms, which can fully relax then in every direction and give us the true energy barrier for the jump from one helium atom, of a helium atom from one energy minima to the next. So this can go into an equation for the diffusion, the activation energy here, and then this is just the vibrational frequency, which can be calculated from the normal modes. And then we can get diffusivities, and these can then go into the forward models for the thermal chronology. Here's the overview slide I showed before, but now I've overlaid the types of codes I use. It's very clear I use VASP all the time for most of these calculations. There are cases where we have used ATAT, and this is mostly to look at, make sure that the order that is induced from an artificially small computational cell does not affect the final answer the physics that we're interested in. Even though I've used VASP for publishing, we have explored other types of codes just to get a feel for how these affect the physics in our system. Mostly what we prefer to do is calculate things directly to compare with experiments. So for example, when we do spin transition, we will fix the volume at multiple volumes for both high and low spin, and then calculate fit these with an equation of state and calculate the enthalpy at where the curves cross. So this allows us to have an independent transition pressure, which can be compared to measurements that come from Mossbauer and XCS spectra. The reason, sometimes though, it's beneficial to calculate exactly what the experimentalists are measuring, and we've done that some. Jane mentioned this yesterday, calculating the quadrupole splitting in perovskite. We did this using Wien, so the motivation for us to switch codes is just that the other code can do something that the current code can't, and in this case, we needed the all electrons so that we could calculate the electric field gradients and get the quadrupole splitting. So in thinking about support from experts, I mean, always more support for computational theory. Just things that I have had to learn have been, ATAT, the nudge elastic band method, the Mossbauer modeling with the quadrupole splitting calculations, just to give a few concrete examples from my own research. Code-specific support, documentation. Do we want money for a technical writer to make sure the documentation is as good as it can be? Example input-output files, help interpreting the output. And then support installing, maintaining codes. Courses, this has been mentioned a lot with the slides and videos, where it can vary from all levels, and it sounds like a lot of us have this if we just have a repository for it. And then also support for computing, for making the most of our computational resources. At MSI, you guys have a great resource here, but for those who don't have that sort of support, what are good scripts? How can we optimize our codes, et cetera? The hardware needs, I mean, mine are pretty modest. A lot of the spin transition work, it's 20 atoms, it's maybe 4 processors, maybe using 20 to 30 nodes. When we get into the diffusion calculations, these can range from 150 to 200 atoms. These can take weeks to relax, and then when you do a nudge elastic band calculation, you need the number of boxes for images, so that this can get a little more computationally intensive. But it's not outside the realm of what's available to us in all these different places. And so thinking about me going forward is that eventually I might have my own group in the future, and so what I would really want is a fully administered cluster with dedicated nodes that I can always get on when I need them, and some flexibility. But it sounds like there are many options out there. We don't need dedicated hardware through NSF through this, so our money is better spent elsewhere. Software, we've talked about this. Obviously, better treatment of D and F electrons, especially for high pressure research. I know this is in development, and you all know evidence for that, so I can skip that. Tutorials for education. We've high pressure benchmarks, example files, something where we can send students and say, this is the correct answer for this at this pressure. removing the black box, we talk about this a lot for DFT codes in the physics, but it would also be useful for the computer science behind the codes, because we often use that as a very black box. And so if we want to create more educated users in our community, making sure that they understand what is MPitch, what is MPI, what does FFT mean, what are some of these concepts. And then if we can target, there's been a need, it seems, that there aren't enough people with expertise to do a lot of coding in this country. And so if we can target people at sort of my level where they might have the physics experience, but giving them the tools so that they can learn the coding or vice versa. And then just to summarize kind of some of the main things I think are important for infrastructure, code and software development, we've talked a lot about that. I think it's very important. Some sort of community for sharing and developing our expertise, as Boris was talking about earlier. I think that's really important that we have somewhere we can all go to, if it's online or some sort of virtual place we can go for this information. And then continued workshops and meetings like this. So, thank you.
So I'm surprised about the helium calculations. Do you see any activation barrier because it's a closed shell system?
We do see an activation barrier. It's not.
How is it incorporated in DFT that is notoriously complicated, like argon, helium, all the last column elements? So I was wondering what the interaction is that you actually see. It should be only van der Waals, which I think is not in DFT necessarily well represented. So the meaning of these activation barriers in terms of chronology, what does it mean in this relationship?
I think a lot of what we're seeing in the activation barriers, and maybe Udo can add more to this, is just the size of the structure of the open channels that it's moving through. Yeah, and so the Zircon has these nice wide open channels, and in our results, which I couldn't show because there's just not enough time. I mean, there's almost no activation barrier there. It just kind of falls through. In apatite, the channels aren't as open, and so it's just the geometry that it's moving through.